So, let us start this lecture with a thought process what is very much inherent in our scriptures, that is love for mother is great virtue, love for motherland is definitely a greater virtue, love for humanity is the greatest virtue to be acquired in our life, so that we can have a very good success in our life. So, as usual, let us recall what we learnt in the last lecture. So, if you recapitulate that, we discuss how the J.P. Joule could manage to find out the first law of thermodynamics, which states that whenever a system undergoes a cyclic process, however the complex cycle may be, the cycle integral of the work is proportional to cycle integral of the heat, right. And that law was originally put forwarded for the cyclic process, and of course, it was based on series of experiments. Later on it was derived for the non-cyclic process, because the cyclic process consists of several non-cyclic process, and in engineering application there will be several non-cyclic process we need to analyze. Therefore, we also derive a relationship between the work and the heat, right, and also rather among the work, heat and energy, and that we say that dq minus dw is equal to dE. If you look at, that is the first law of thermodynamics, what we have derived is dq minus dw is equal to dE, and this law is valid basically for non-cyclic process, If you look at what we are dealing now, basically is a control mass system, right. In the control mass system, except few exceptional cases, most of the times will be the change in kinetic energy and change in potential energy will be what? Will be negligibly small or 0, right. Therefore, we can say that when change in kinetic energy is 0 and change in potential energy is 0. So, therefore, this equation we can write down as dq minus dw is equal to du, right. Only this is valid, and that is meant for control mass system, But is there any control mass system where you cannot really change, or you cannot take this assumption that change in kinetic energy and potential energy? Is there any example coming to your mind? Yes or no? Right? Let me give you example, one of them. Suppose somebody has slapped you, okay. So, I want to analyze, particularly if your color is good in the sense color is yellow or the white, then if the slap is intensity is high, what will happen? That your skin color becomes reddish, right. Okay, yes or no, on the slap on your cheek or something like that. So, I want to analyze that what happens to changes. If you look at what happens to the changes, is it work being done? or is heat being generated there or not. Whether I can apply, whether I can manage to assume the change in kinetic energy will be 0. Potential energy of course I can, but change in kinetic energy you cannot say it to be 0, right. Yes or no, right. So, think about how to analyze that, and there might be several other occasions where control mass system in case of control mass system you need to consider the change in kinetic energy, change in potential energy as well, but most of the cases it is not, right. So, let us now take off some very basic processes like what we have seen earlier, like control volume processes, what we call isochoric, and we will be looking at also the constant pressure processes, isothermal processes and adiabatic processes and others, right. We will see how we can apply this first law of thermodynamics. Let us consider a case, a container which contains some kind of, let us say, gas at temperature 300 Kelvin and 100 kPa, and it is a rigid, like no change in this changes. So, that if it is rigid, what is happening, like there is no work done, PDV work basically, and it is also insulated all the places here, right. However, the other side, one side of this chamber is in contact with a heat source whose temperature will be higher, right. If I say this temperature heat source is 1000 Kelvin, right, what will happen? The temperature gradient will be very high. Then there will be change in the temperature of this gas. If I say this is my gas, right, there will be change in temperature of the gas of the container, right, yes or no, because heat being transferred, yes or no, right. If the temperature is changing, then the process, can I call it as a reversible process? Because it will not be in equilibrium, because gradient is much more, right. Okay. So, and also I cannot reverse the process back, but however, if I consider the process, let us say this temperature to start with, here it is 300 Kelvin, I will say this is something 305 Kelvin, right. So, the temperature gradient is very, very slow, I mean very, sorry, not slow, rather it is the temperature gradient is small, right, and then that will be taking place, and then if you want, you can reverse this process, and by changing the system, that means you can take the heat out and then do that something. So, therefore, if it is a slow process and it will be attaining a quasi equilibrium or what I call quasi static process, right, then we can call it as a reversible process. Then the state from 1 to 2 can be described in this PV diagram. Of course, as the heat being transferred, there will be increase in the pressure also, because this is a what you call constant volume, because volume is not changing. So, therefore, the pressure will go up, and so also the temperature will go up, and while the volume is remaining constant, right. So, then what we will do, we need to find out what is happening here, right, and kind of thing, apply the first law of thermodynamics. When we will apply the first law of thermodynamics, if you look at, that is the work done, in this case the PDV work will be 0, and we are not putting any shaft work. So, therefore, work done will be 0. And if you look at this first law of thermodynamics, what for a what you call a non-cyclic process, that is dq minus dw is equal to du, and in this case the dw is 0. So, therefore, dq between state 1 and 2 will be nothing but change in the internal energy between 1 to 2. As you are giving heat, therefore, in this case the internal energy at the state 2, that is U2, will be greater than the U1. Okay. Now, this heat, if I know these properties, at let us say from a table and other things, it will be easier to evaluate. Let us say from the steam, instead of gas we are considering a steam. Now, if it is steam, it is an ideal condition, then one can use dq 1 by 2 mCv T2 minus T1. I will be knowing the temperature T2, and of course T1 is known, and if I know this Cv, specific what you call heat at constant volume, then I can evaluate. Now, what is that? All those things we will see. Keep in mind that it is very important to know this internal energy at both the state. Either one can use the what you call the tabular data, or we can assume it ideal gas, and then one can evaluate, right. So, let us look at what you call some processes, irreversible processes, and as I told in the very beginning that if the temperature of the heat source is very, very large as compared to the system temperature, right, then the temperature gradient will be higher. As a result, the process will be reversible, and this path cannot be traced in a PV diagram. Generally, we use a dashed line to show the process, irreversible processes in a process diagram, like PV diagram is a process diagram. So, let us consider another what you call constant volume process. In this case, paddle wheel is there, and then it is of course connected to usual. We are just trying to look at the thermodynamic way of work, and when it is rotated, this kind of things through the mass is lowering down against the gravitational field. Some work is being done, and as a result, what will happen? If it is the gas, the temperature will be going up, yes or no, because some work being done here, right, and there will be this thing. So, and also it is insulated, no heat is passing through that. This is, if you look at dq is 0, and this process is basically reversible or irreversible. What is this process? This process cannot be reversible, right. You can make this paddle wheel to rotate, right, externally. That means work is done by the surrounding on the system, but however, you cannot do the other way around. The like in this case, if you are doing that, the pressure will go up, and then is it like this what you call paddle wheel will be start rotating if you won't give the external work, it won't. That means the work cannot be from the system, will be done by the system, right, on its surrounding. It is not possible in this case. So, therefore, this process will be irreversible one. And let us consider the another case, which is control volume process, and instead of paddle wheel we are putting a resistance, and which is connected to a battery. And if you look at this process, because we have taken this as a system, so is it a work interaction or a heat interaction? It will be basically the work interaction, right, because the electrical resistors is already included in the system boundary. So, of course, we are considering this as insulated. So, heat interaction will be from the system to surrounding will be 0, and this process is also irreversible isochoric process. It is not possible to reverse the that means the system will be reversed back to its original state after the interactions, right. So, let us now, and this process is basically can be described in a PV diagram generally people use a dashed line to show the process as irreversible. This is a convention, like, but in principle one cannot really describe the process, irreversible process in a process diagram like PV here. So, if I apply the first law of thermodynamics, then that will be du is equal to minus dw, because the dq is 0, right, in this case. So, therefore, the work done will be equal to change in the internal energy, right, change in that U2 minus U1. Keep in mind this work is negative. What is the meaning? Meaning is that work is done by the surrounding on the system. According to convention, when work is done by the system on a surrounding, it is positive. When the work is done by the surrounding on the system, it is negative. So, therefore, it happens to be negative, and so therefore, there will be increase in the internal energy of the system, right. And we have already introduced the concept of specific heat at a constant volume. But what do you mean by that? Let us take an example. I am having 1 kg of water, okay. 1 kg of water is equal to 1 liter, you can say 1 liter of water is equal to 1 kg, because, and then I am going to heat it, from let us say 25 degrees Celsius to 35 degrees Celsius. So, how much heat I will have to give, right, or how much heat it will be containing, the temperature has gone up, that means, so it will be, if you look at, it will be let us say certain amount of heat, okay. And suppose instead of 1 kg of water, I will take 1 kg of water and rice, okay. So, I will give certain amount of heat and I will see that temperature is going from 25 degree to the what you call 35 degrees Celsius. What is the amount of heat I will have to give? Any idea? Is it higher or lower? What I should give? I mean, I just say, whether it is a higher or lower, or it will be same. It can be same also, right? Will it be same? Suppose I will take, let us say 1 kg of iron. I want to increase its temperature from again 25 degrees Celsius to 35 degrees, 10 degree difference. So, what will be amount of heat? The amount of heat for heating iron or the this thing will be basically say around 4.5 kilojoule, whereas from the water it will be something around 41.8 kilojoules, right, okay. Let us say like the number may will vary little bit. Suppose I will take another example, like I will take 1 kg of air, I want to heat it from again 25 degrees Celsius to 35 degrees Celsius. What it will be? And if instead of 25 degrees Celsius, right, and to 30 degrees Celsius, I will say I will heat it 25 degrees Celsius to 250 degrees Celsius. What will be the heat I will have to give? You assume that I am heating in a constant volume, let us say, right. So, what will be in this case? This is another, like this last two example I have given air, and where the temperature is one order of magnitude. In one case is the 10 degrees Celsius, other case is the 100 degree, difference. 250 to what I told? No, let us say 25 to 35, other is let us say I can say like something 20 what you call 250 to let us say 350 degrees Celsius, okay. I think I changed my this thing 250 to 350, 100 degree Celsius, that is 10 degree Celsius difference, okay, right. So, what will happen? Should I give more amount of it or less amount of it? Actually, if you look at, if you increase temperature, but in case of air, you will have to give more amount of heat, okay. I am just telling you, just look at it, the values, and then see that. What it indicates? So, this example from this one you can say that means each substances, one is water, other is iron, and water is another water and rice, like together, and air. So, if you look at the each things are having different capacity of heat for the same change in temperature, if you consider. So, basically that means we need to look at about how much change in the temperature is taking place, because per unit mass of the substance for degree Celsius or Kelvin, right. Why we need to know? Because whenever a system is interacting with its surrounding, there will be change in the temperature, provided some heat interaction is taking place, and if it happens to be at a constant volume, then what will happen? Then we need to define a specific heat at a constant volume as the amount of energy as a heat required to change the temperature per unit mass of substance by 1 degree. 1 degree, it may be 1 degree Celsius or 1 Kelvin or 1 degree Fahrenheit or any other things, okay. So, if you look at what we are discussing is basically a what you call can be specific heat at constant volume can be expressed mathematically as Cv is equal to dou q by dou t when volume is remaining constant, right. So, if you look at in the constant volume, right, we have seen the change in energy is basically due to the change in heat, right, kind of things. And therefore, we can write down for isochoric process dq is equal to du. So, then Cv is equal to basically dou u by dou t at constant volume, right. So, this is a property, means it does not depend on the path what it is taken, right. It is a properties of a substance, right. So, let us look at it how we can utilize this property to evaluate what you call interaction between system and surrounding, and in this example we are considering insulated and rigid container of volume 1 meter cube, which contains helium at 20 degree Celsius and 100 kPa, and a paddle wheel rotated inside container raising helium gas temperature to 60 degree Celsius. And of course, we can assume that helium gas obeys the ideal gas law, that is P v is equal to nRT, and we need to determine the work done on the helium and final pressure what it would be, and you can take the Cv as 12.4717 kilojoule per kilomole Kelvin. Like it can be, in this case it is for kilomole, and one can also express this in terms of what you call in terms of kg also, like kilojoule, kg and Kelvin. In this case I am using this kappa as a symbol to differentiate which one you are using. So, if you look at, this is the diagram which contains the helium gas, right, and it was at 20 degrees Celsius and it has gone to 60 degrees Celsius at stage 2. So, you need to basically find out, and this is insulated. So, no heat being transferred here, dq is equal to 0, and it is rigid. so that there is no PDV work going on and only the shaft work going on because of rotation of this wheel. And if we just apply the first law of thermodynamics, you will get the change in the work between state 1 and state 2 is nothing but change in the what you call internal energy is equal to n CV dt, right. And n is the number of moles, and that you can get by using the ideal gas law, because we will be using this ideal gas law to what you call obtain this number of moles and keep it in a control mass system. So, number of moles remain same. So, we can obtain this number of moles at state 1, P 1 is given, right, and V 1 is also volume is given 1 meter cube and temperature is given, right. So, you can find out very easily that thing, and keep in mind that this is your universal gas constant, right. So, the universal gas constant is here and temperature given, you can find out very easily, that is something 0.41 kilomole. And the change in the work done is basically nothing but your what you call number of moles into the CV and change in temperature 60 degree minus 20 degree, and that is 20.4685 kilojoule. You just substitute values, and the work done is equal to the change in the internal energy, and which is having a negative sign here, which indicates that work is done by the surrounding on the system, right. So, therefore, it is negative. And by using, because we know the what you call the temperature T2 and we know the temperature T1, right, and we can also find out the pressure P2 as we know the pressure P1 using the ideal gas law. So, you just substitute these values, because all are this is known T2, T1, and then you just substitute these values, and then you will get this 106.82 kilopascals. Of course, if you look at the pressure, its change is very, very small, that is something 6.82 kilopascal, because the temperature change is not much due to the work done. So, therefore, the pressure change is very, very small in this example. So, let us look at isobaric process, which is a constant pressure process. And if you look at whether it is an ideal or not, but several processes in engineering can be considered as an isobaric. For example, like when you add heat in either in a diesel cycle or in a gas turbine engine, or even in your burner, like LPG burners, you add heat, like, and that process also takes place at a constant pressure, because the atmosphere is acting, even though there is expansion, but that expansion is not really what you call always with the constant pressure. So, that can be mimicked as a isobaric process, right. And of course, there might be kind of situation where it won't, there might be some losses, but what you can see, at least under ideal condition, you can assume the heat addition in several kind of what you call engineering applications as a constant pressure. Even you will see in the steam power plant, as when we will discuss about Rankine cycle, we will see the processes in a boiler one can assume to be a constant, occurring at constant pressure, because the vaporization will be taking place, right. And so, saturation pressure and temperature will be remaining constant, So, now let us consider again piston and cylinder arrangement in which the gas is there at pressure dP, P plus dP, that means this pressure is little bit higher than the pressure acting by the atmosphere on the piston, and there is no friction in between, and when you add a heat source. So, what will happen, this pressure, let us say it is started with the same pressure that the atmospheric pressure which is acting, then because of heat transfer, right, from the heat source, the change in the pressure will be very, very small. As a result, the piston is moving up and doing some work, and as a result, this is very, very small. This dP is quite small, Sometimes you can say it is tending towards 0 kind of things, that is not exactly 0, it is very, very small. That means, this dP is compared to the actual pressure is very small. For example, if it is 100 kilopascal and if it is, let us say, change in pressure is 1 pascal, right, then we can call this system is in quasi equilibrium, and if you remove that thing, and then as there is no friction between the piston and cylinder being assumed, then we can call it as a basically a reversible isobaric process, because it is all the time in the state of equilibrium. And in real situation it need not, because you cannot have a piston and cylinder where the friction won't be, the friction will be there. Although we can minimize the resistances of the friction, in the actual system to reduce this work being lost due to the friction. But however, here we are considering there is no friction between the piston cylinder, and it is the process is occurring very slowly in a quasi static way. So, therefore, we call it as a reversible process. And there is another process, we can say that saturated liquid, and as you are giving the heat here, right, and the heat is slowly heating this, then what will happen? It will be vaporization will be taking place. This is the what you call liquid and this is vapor, and if you and some work is being done, and if you remove this heat from here, and then it will be condensed and come back. So, that you can call it as a reversible isobaric process, as the system can move in a reverse way and reach its original state, right. So, therefore, we call it as a reversible isobaric process. And this process can be easily described from the state 1 to 2 in a process diagram PV. Of course, in the process there will be change in what you call temperature, and as I told that just to give you a idea that in this saturated liquid vapor region where the heat addition is occurring, but temperature is remaining constant. However, the pressure also will be remaining constant, and therefore, that will be also known as the isobaric process. So, if it is isobaric process, then work done will be basically integral of P dV, and pressure is remaining constant. So, you can take it out, and that will be equal to P into V2 minus V1. And we will apply the first law of thermodynamics, which is equal to du is equal to dq minus dw, and there is no shaft work, only the PdV work. So, therefore, I can write down dq minus PdV. So, what I can do, I can take this, then we can write down dq is equal to du plus PdV, and keep in mind the pressure is remaining constant. Therefore, I can write down differential of this du plus PdV, because like if I expand this term, what will happen? This term, if I expand this term, this will be du plus PdV plus Vdp, and dp is 0. So, therefore, this term is equal to that, and if you look at by definition, the enthalpy is u plus Pv. So, therefore, the dq is equal to the dH. Basically, I can write down dq is equal to dH in case of for isobaric process, right. And this specific enthalpy also can be written as enthalpy per unit mass, or it can be also known as enthalpy per unit mole, right. H naught I can write down H per n is equal to U naught plus P V, right. This is per unit mole, enthalpy per unit mole, like kilojoule per, you can say, kilomole unit. So, keep in mind that for a constant volume process, what we have seen? We have seen dq is equal to du. In case of isobaric process or a constant pressure process, we have seen dq is equal to dh, change in enthalpy, right. So, this is for the reversible process, and we have seen that heat interaction is across the boundary is basically change in enthalpy. And let us look at energy balance for a constant pressure during expansion and compression processes, right. Because there we have looked at kind of heat interactions, right. And here we will look at work interaction, where there is a shaft is being rotated, the paddle wheel, and this is the gas, and it is basically insulated. So, what will happen? There will be change in the what you call is temperature and other things, right. And this process is basically irreversible process, as I told that the work done on this paddle wheel cannot be reversed back. That means system cannot really produce the work done by the rotation of the paddle wheel of its own, right. Because in this case the work is done by the surrounding on the system, like you will be having a motor or a pulley or something to rotate this one to, so that work can be transferred to the system. And we can also take another example, which is electrical resistance, and it will be connected to battery, and as usual this will be work will be done on this system, and this is also insulated, and this is a reversible process, this is an irreversible process. And for adiabatic wall dq is equal to 0, we can use the first law of thermodynamics, therefore the internal energy is nothing but your minus dw, which is equal to p dv plus d shaft kind of things. So, if you look at this case then the shaft work will be p d what you call du plus p dv, because there will be piston will be moving and there will be some work, and that is nothing but your what you call change in enthalpy, right. And again the shaft work is negative, and which indicates that what you call the work is done on the system, and which is if as a result there will be change in enthalpy of the system. So, the shaft work is always a negative quantity in case of a constant pressure process. So, we can define the similar way what we have done for the constant volume, that is specific heat at a constant pressure. So, that is defined as a quantity of heat required to change the temperature of a unit mass of substance by 1 degree. So, the Cp, if you look at, it is nothing but dou q by dou t at constant pressure. We have already seen that this dq is equal to dh for a constant pressure process. So, therefore, that is basically Cp is equal to change in enthalpy per unit change at a constant pressure per unit mass also, or it can be also per mole, right. the total interaction for a change in temperature when T1 to T2 can be estimated as Q is equal to m Cp dt, and keep in mind that this Cp like we need to know at what you call at a particular temperature, and as I gave an example in the very beginning that it may be dependent on temperature also, right. So, we will see as we go along. The molar heat capacity at constant pressure is defined as basically Cp kappa as dou H by dou T as P, and this unit is kilojoule per kilomole Kelvin, and in this case per mass this will be kilojoule per kg Kelvin, right, kind of things. The unit is that. So, if you now we need to look at how we can evaluate these properties, and both the specific what you call heat at constant pressure and constant volume, these are property of the system, right. So, these has to be, we will have to learn how to evaluate, so that we can estimate the heat interaction or the work interaction whenever a system will be interacting with surrounding. So, let us look at like internal energy and enthalpy and specific heat of an ideal gases, and we know that H is equal to UPV from the this thing, and we have also know that this PV is equal to RT from ideal gas law. So, then we can say that H is nothing but U plus RT. And let us look at an experiment which was conducted by the Joules, and he took some what you call two vessels which is at a constant like air he has taken as a very high pressure here, and it is and another chamber he has taken at a evacuated or the vacuum kind of thing, it is connected with a valve, and he put into a water bath or this thing and measured its temperature, and it opens these valves. What will happen? The high pressure gas will rush into the evacuated chamber, and there will be change in pressure, right, and there will be also kind of effect. And what will happen to this temperature of the bath? What will happen? Because if you look at pressure is changing, and so also what will happen to its temperature? And he allowed this thing to occur for a allow this process, anything is happening, so that it can be registered between this what you call process and this water what it is having. So, he observed that there is no change in the temperature, right, and of course, he has considered this air gas at a high the pressure such that it can be treated as an ideal gas, right. And therefore, he concluded that there is no change in temperature, therefore, internal energy is basically is a function of temperature only, it is not a pressure, because there is a change in pressure here, right. Pressure become higher and it become a lower due to the expansion process, but however, there is no change. So, therefore, he says that internal energy is a function of temperature, and that is valid only for an ideal gas law, ideal gas. But however, if you conduct the same experiment at much higher pressure where you cannot treat the gas as an ideal, then you can find that it is a function of not only the temperature, but pressure. And then one can say that the enthalpy is also a function of temperature, and Cv, Cp are also function of temperature for ideal gas, right. So, that we will be considering. So, if you look at if our Cp and Cv is changing with respect to temperature, then we will have to learn how to evaluate it, because the change in internal energy will be basically Cv dt, and Cv is a function of temperature. This is a temperature, it is dependent on temperature. And if we integrate this thing equation, I can get between the two system du is equal to du2 minus u1 and Cvt and dt. Unless I know this, what you call how this specific heat is dependent on the temperature, then only we can really integrate, otherwise we cannot. Okay? Or we can take average temperature, average specific heat values at a particular temperature, then you can integrate, otherwise difficult. So, to do that. And similarly, we can also find out is equal to dH is equal to Cp T dt, and we can integrate this to get 1 to 2, 1 to 2 here, and then we can evaluate the dH 1 to 2 is equal to S2 minus H1 and 1 to 2 Cpt dt. So, these we need to see that how we can have these properties of the specific heat and specific heat at constant pressure and constant volume. So, if you look at low pressure, all the real gases approach the ideal gas behavior, and therefore, their specific heat depends on the temperature only, right, as Jules have conducted experiment and found out, and the specific heat for of the real gases at low pressure are called ideal gas specific heats, or the zero pressure specific heats, are often denoted by Cp naught and Cv naught. If you look at how these properties are changing with respect to various what you call gases are shown here, the Cp versus the temperature. If you look at monoatomic gases, does not change, and whereas the biatomic gases do change, but not much as compared to the triatomic gases or kind of things. And question arises, if you are evaluated at different temperature, particularly high temperature zone, this curve is very steep. So, how you will evaluate it? So, you need to relate this thing in terms of certain maybe third order or some polynomials, and curve fit you can do, and then you can evaluate. And UH data for a number of gases have been tabulated, right, you can use the tabulate value, and these tables are obtained by choosing an arbitrary reference point and performing the integration by treating the state 1 as a reference state. For example, like generally, if you look at the temperature 0 Kelvin is taken as a reference here, because all this reference temperature, internal energy, enthalpy is 0, and at different temperature it will be different values, like kind of things. So, it will be a function of temperature. So, if you can take a reference and then you can do, it will be easier, but however you should know how it is varying, right. So, let us see that how we can do that, and internal energy and enthalpy change, and when specific heat is taken as a constant at an average, because we need to do a calculations. So, therefore, we can take an average values, right, because all the time whenever system is interacting surrounding, there will be change in internal energy or change in enthalpy. So, therefore, we need to evaluate, and we can take that U2 minus U1 C average and T2 minus, and this you can do only when the changes is not much. For example, if you look at the state 1 here and state 2, it is actual process is taking place here, but if I take a approximation, this is a what you call linear, I am assuming, but you are making some error between that. Then I can take average values here at T average and Cp average, then I can take it out and integrate very easily and then evaluate. So, this is true only for a small temperature intervals, right, otherwise it will not be. And if you let me just give you that always you may feel that whether a constant volume process is there, right, Cv, temperature change from 20 degree to 30 degree Celsius, and there is a constant pressure process, temperature also change in 20 to 30 degree Celsius. If you look at change in internal energy is remaining same, whether the process is constant volume or a isobaric process or constant pressure. So, therefore, we need not to get bogged down that whether the process is this thing, the change in internal energy will be remain same whether the process is constant pressure or constant volume. So far the change in internal energy will be always related to the Cv dt, and the change in enthalpy will be related to the Cp dt. So, it is does not really depend on the whether the process is constant volume or a constant pressure or any other process. Okay. So, that you should keep in mind, you should not get bogged down by the definition of the Cp and Cv. Okay. We will stop over here, and in the next lecture we will see how to handle also for the solid, because we have discussed the Cp, Cp for the gases, and we will handle also how to for the liquid and solid which are incompressible in nature. Thank you very much.